Thank you very much, Nathan. Let me start by thanking, once again, the organizers for putting together such a wonderful conference and for giving me the honor to speak here today. And my talk today will have two parts. The first part is based on work done with Song He and Ellis Zhuang. Song is a postdoc, and Ellis is my graduate student. The second part of the talk will be based on work to appear with Humberto Gomez, the same Humberto Gomez that did the three-loop calculation with Carlos in the previous talk. So he's been very busy lately. Very good. So today I'll be talking about scattering equations, and we have seen in this conference many talks producing formulas for new objects. So today I decided to change the topic, and instead I'll concentrate on a new formula for a very old object. What is the very old object that I want to talk about? Well, it would be great if I could move the... is there any way to get rid of the little hand in the... Yes, thank you. Very good. Yeah, I couldn't do it from here. So I gave you time to think about what the old object is. I hope everybody figured it out. It's the S matrix of massless particles, of scalars, gluons, and gravitons. This is something that we learned in quantum field theory 101 as graduate students. So why look for a new formula for this? Feynman gave you Feynman graphs, and that does basically everything we need. But the first indications that there is something deeper behind Feynman diagrams or behind scattering amplitudes came in the 80s when Park and Taylor, just out of the need of calculating amplitudes for colliders, they studied the scattering amplitudes in Yang-Mills, where you have the data that you have to use are momenta for each of the particles, the polarization vectors, and the color structure. And they studied the simplest non-vanishing amplitudes at tree level. Those amplitudes are the ones that have two negative helicity gluons and the rest of the gluons positive helicity. So these are the simplest amplitudes you can compute, and they were very brave, and they computed them. And even for a small n, there will be many, many diagrams that you have to compute. Of course, they didn't expect it, but in the end, a miracle happened. Using some special variables, which some people like to call nowadays magic variables. Now you see why. So you write the momenta in this form with two complex variables, ZA and ZA bar. And the polarization vectors can also be written in a similar form that depends, of course, on the helicity of the particles with some reference spinors, with some reference variables. You find, or Park and Taylor found this miraculous formula where this is a trace of, say, generators of the group in some representation, say the fundamental representation, and these are the color indices of the particles you have. Now, I would like you all to memorize that formula. Okay? That formula is going to be the answer to a question I'll pose later in the talk, so I hope everybody will remember. So does this miraculous formula, or this miraculous simplification, occur for other helicity configurations? Well, that's a very natural question. People tried. Nothing came out at first. In the 90s, a crucial insight came from Nair. He realized that this Park-Taylor formula looks like the correlation function of some particles on a CP1. But that idea lay dormant for many years until Witten in 2003 figured out how to extend this to other helicity configurations. The CP1 was somehow a CP1 that could serve as the world sheet of a string theory whose target space was Penrose's twistor space. And depending on the degree of the embedding into Penrose's twistor space, you could get other helicity configurations. And then you map to four-dimensional momentum space to get the amplitudes. And this was all done for gluons. And this gave rise to twistor string theory. So the natural questions at the time, and since then, have been, is there a similar formula for gravitons? And what about for scalars? Is there a formulation in any dimensions? Or is it special to 4 dimensions? After all, we are calling these variables magic variables. And if they only exist in 4 dimensions, then all the magic is only there in 4 dimensions. And if such a formula can be found, can it work at tree and loop levels? That would also be surprising, because at loop level, you would expect to have genus 1 Riemann surfaces. And we know all the baggage that comes with genus 1 Riemann surfaces. Elliptic functions, we will have theta functions all over the place. How can that reproduce a simple loop amplitude that is supposed to be just, say, at one loop, dilogarithms? That seems very hard. So, given that we want to work in any number of dimensions, we have to start from scratch. We don't have the luxury of the magic variables. So we have to go back, and in the search for the new object, we start with something very, very basic, the space of kinematic invariants. So the kinematic invariants are the following: SABs, these are the usual Mandelstam variables, the sum of the momenta square. They are all null vectors. As I said, we're going to be dealing with massless particles. And now we consider 4 particles. If you don't know what you're doing, you always start with 4 particles. Now, the Mandelstam variables are S, T, and U. They satisfy this constraint. And this is a space of kinematic invariants. And the amplitudes should have singularities as S equal to 0, T equal to 0, or U equal to 0. And those correspond to these lines in this space. Now, the space by itself doesn't really care about these lines. So my conclusion is that this space doesn't know much physics. Now, you may ask, well, is there any space that knows more physics than this one? Well, in this audience, I'm sure you all are thinking about one particular space. We're looking for a space that has 3 singularities. Well, as I said again, I'm sure that if I ask, 90% of you will come out immediately with the following answer. It's a moduli space of genus 0 Riemann surfaces with 4 punctures. That moduli space has exactly 3 singularities, 3 singular points. What are the singular points? Well, at a generic point in the moduli space, we have a Riemann surface, a beautiful object with 4 punctures doing nothing interesting. And at the singular points, the Riemann surface degenerates and produces some sort of factorization. That looks exactly like what we're looking for. If only we could associate to each of the punctures the vectors of the external particles. If we could do that, then we could connect these things to some scattering amplitudes and piggyback on the fact that this space has the correct singularities. And instead of using this, we could use this space. So the conclusion is that Riemann knows a lot of physics. Of course, we knew that already. Riemann knew a lot of physics. But in this case, what I mean is that Riemann surfaces and their moduli space knows a lot of physics. And what we want to find is a way to map this into the null con in d-dimensional momentum space in such a way that we can associate punctures to the external momentum. So here is how we're going to do it. We construct a one form, a Lorentz vector of one forms, such that it has only singularities at the punctures, and the residue is equal to the momentum of the particle corresponding to that label. Moreover, we want this whole thing to map into the null con, so we're going to impose that the Lorentz scalar quadratic differential written here is equal to 0. Okay? So those are the conditions we're going to impose, and, well, that gives rise to something that we call the scattering equations. The first condition is trivial to satisfy. In 5 minutes, you write, or even less, you write down what the most general formula has to be for this rational function that together with the differential produces the Lorentz vector one form we're looking for. Now, this function seems to have a pole at infinity, but the residue at infinity is a sum of the momenta. So if we're dealing with data that satisfies this momentum conservation, which is physical, then there is no pole at infinity. And our form here satisfies the conditions we want. Now, the quadratic differential vanishing means that this rational function has to vanish. This is a rational function that vanishes at infinity, and therefore, if we can show that it has no poles anywhere, we are done. The residue of this at some particular location of the poles, say at sigma A, It's very easy to calculate, and it gives this formula here. And the constraint we have to impose is that the residues vanish for every possible pole. So these are the scattering equations, and they link points in CP1 to the space of kinematic invariance. And they nicely map all the singularities of the modular space of Riemann surfaces of genus 0 to physical factorizations. Now let me discuss a little bit about the history of these equations. As it turns out, I was surprised to realize that they are even older than I am, because they were introduced, or they were found first, by Fairley and Roberts in an unpublished work in 1972, when string theory was still called dual models. Then in 1988, these equations appear again in the work of Gross and Mende in the study of high energy scattering of strings. In 2004, Witten also found them when he proved parity in the twistor string theory. In 2012, they appear again in Wilson loops, and I also found them in trying to find a derivation of the BCJ formula, starting with the Witten RSV formulation of scattering amplitudes. Okay? So we fell in love with these equations. They seem to know a lot of physics. All you need to do then is to think that, or to believe that there is a formula that computes the full S matrix, or the full three-level S matrix of gravitons in d dimensions. A formula like this must exist. So it's a formula where you integrate over the whole modular space on the support of the scattering equations, and all you have to do is to find the integrand. That's the job. Of course, if you believe that such a thing exists, then it's not difficult to find it. The constraints, or the hints we had, were permutation invariance, gauge invariance, Weinberg-Soft theorems had to be satisfied, and it had to be multilinear in the polarization tensors. So we came out with a matrix, and it's a matrix that encodes all the information that you would like to have in one object. So the kinematic invariance, kinematic case with polarization vectors, and here polarization vectors with polarization vectors. Here I'm thinking about gravitons, the polarization tensors, as a product of two polarization vectors, because it's easier to think about polarization vectors first. And the difficult part was to come out with what these off-diagonal pieces here in this matrix were. Here is the answer, but I'll try to convince you why this is the right answer. Now, this is a matrix, and what we need is just a function, a rational function of these objects. So here is a proposal. All you do is to compute the determinant. Why the determinant? Well, you needed something that was permutation invariant in all the entries, and the determinant will give you such a thing. You need something that is gauge invariant. Is this gauge invariant? How do we see gauge invariance, which is something complicated usually to see in regular Feynman diagrams? You have to work hard. So here what you do is say, you replace the polarization vector epsilon1 by k1. So you see that here all this row, first of all, this C, as I defined it before, becomes 0 due to the scattering equation. This is one of the scattering equations, so this is 0. Here you get k1. All this is replaced by k1s. Here too. And now, if you quickly look at this matrix, you will realize that this column is identical to this column, and therefore the determinant vanishes. So you get gauge invariance almost for free. So here is a proposal that the full three-level S matrix of gravity in any number of dimensions is just given by this. So factorization has been checked, and all the standard properties that this formula has to satisfy has been proven to be true. But how about gluons? Okay, we started the whole story with gluons, with Young-Mills. Well, there is a hint. The matrix we constructed is antisymmetric. Well, everybody knows that if you have the determinant of an antisymmetric matrix, that's the square of something. It's the square of a Pfaffian. And here it is. Now, if you have heard talks about amplitudes for the past 20 years, you have heard that gravity is the square of Young-Mills. Now, why don't we use it? You say, well, if gravity is the square of Young-Mills, and the Pfaffian and the determinant is the square of a Pfaffian, then it must be that Young-Mills is given by something like this, just the Pfaffian. But Young-Mills also has color. So we need something else here that contains the color information. So that's the question I warned you I was going to get to, so I hope everybody wrote down the answer when I warned you to remember the Park-Taylor formula. Okay? The answer to the question of what to put in here, or what this is exactly what Park and Taylor found. But now this is true for any polarization vectors. It's not even necessary to be in 4 dimensions. We are in higher dimensions where there is no notion of helicity. How about scalars? Well, if the trick works once, of replacing one of the Pfaffians by C, it might work twice. And indeed it does. So you replace it by by 2 powers of this color structure or this Park-Taylor structure, and you get the scalars. So we go from gravity, 2 copies of the Pfaffian, i.e. 2 polarization vectors, put it together to get a polarization tensor, to 1 Pfaffian times the color structure, and we go down to 2 color structures. Now, one of those pieces, if you expand that out, all those traces and all that, one such piece is something that looks like this, and this computes or is a generating function for all the diagrams in lambda phi cube that can be drawn on a plane with a particular ordering, with the ordering chosen here. Okay? But if you remove the color factors, then you get the full answer for lambda phi cube, as Dolan and Goddard proved. All right? So let me now go and conclude the first part of the talk with some further developments. So this is only a partial list, so I'll use the standard apology of all the speakers. So I apologize for the people I didn't have the space to write. And indeed, I didn't have a space because when you're, it's actually smaller than what it looks like here in the screen. My excuse didn't quite work here. But nevertheless, so let me mention some. So here is some of the work that has come out in the past few months. But let me stress this work on ambitwistor string and loop amplitudes in ambitwistor strings, because it's a natural next question. If everything works at 3 level for genus 0 Riemann surfaces, why don't you go to higher genus? Can you do it? Well, they constructed a very beautiful and elegant approach. In this elegant approach, of course, you go and they build a string theory, and when you do your one-loop calculation following the textbooks, you still find something that has elliptic functions, theta functions all over the place, and you still wonder, can this thing really be the integrand of a mundane quantum field theory? Well, what I'll describe now is what I like to call hyperelliptic scattering equations, and this is a work with Humberto Gomez. So let me recap the approach we followed to get the genus 0 answer. We said, first step, construct a Lorentz vector of meromorphic differentials. Here it is. With simple poles only, the only singularities are simple poles at the locations of the punctures and residue Ka. Second step, impose that the Lorentz scalar quadratic differential vanishes. Now, how can we generalize this to higher loops? Now you think hard for a while, and here is the answer. Well, at genus G, first step, you construct a Lorentz vector of meromorphic differentials with simple poles at the punctures with residue Ka and impose that the quadratic differential vanishes. Okay, so here is our hyperelliptic curve, parameterized in some particular way, and this is my best picture of what it looks like, with some punctures sprinkled on the upper sheet and on the lower sheet. And the next ingredient that we need is a meromorphic differential with simple poles at P and 2 points, P and Q, with residues +1 and -1. And this turns out to be unique if you impose this condition. So these meromorphic differentials are known to exist on any Riemann surface. And if we have them, then we can construct this linear combination of meromorphic differentials of these meromorphic differentials of the third kind. So we have this construction, and it's very easy to realize that they have simple poles at sigma A with residue Ka. That's what this thing was doing, has a residue +1 on sigma A. How about at Kn? This object seems to break the symmetry, but at sigma n, all of them have residue -1. So we get a total residue of minus k1 up to minus km minus 1 mu, but by momentum conservation, that happens to be km. So this thing seems to encode all the singularities we need. Therefore, if we take our meromorphic form minus this object, we get a purely holomorphic form on this Riemann surface of genus G. And therefore, it can be expanded in the basis of holomorphic differentials, and with some coefficients that happen to be G vectors. We have G of them. The next step, you say, well, now that we have our form, we impose that the quadratic differential vanishes. That sounds very easy, but I haven't told you what the taus are, what these differentials are. They are the ones that encode all the magic. They are the ones that we don't know how to construct at first, or you might think it's very hard. But luckily, this problem is familiar in physics already, from the study of Cyber-Witten curves, matrix models. In many, many contexts, this problem has arisen. And here is the answer. So you write your one form in this complicated-looking structure. And here I'm putting the punctures on the upper sheet. That's why I put that's why we have this structure. If they were on the lower sheet, we would have a plus sign. Now you would say, but this looks clearly wrong. This certainly has singularities only on the places you told me, right? Because if you're near those singularities, near those points, you get a 0 here in the numerator. The log will produce a 1 over z minus sigma a with coefficient 1, so the residue will be 1. And in this case, you will get minus log of that, so you will get residue minus 1. But how about the original Riemann surface? You haven't told me where the Riemann surface is. This looks like an auxiliary Riemann surface, and indeed, it's an auxiliary Riemann surface of higher genus than the original one. And now we want to embed what we had before into this bigger Riemann surface. Doing so, we get these polynomial equations, which I like to call the embedding equations, together with the quadratic differential vanishing, and these are the hyperelliptic scattering equations, okay? Very good. So quickly, let me give you an example, a genus 0. This is the complicated curve. Well, it's very trivial. These are the embedding equations. They have a minimal solution, and the solution tells us that the polynomial p has a coefficient that depends on the branch where you put your puncture. Here is a form, and here are the scattering equations. They look very different from the scattering equations we started with, but by a simple rational map, as expected, you get the original ones. But have we gained anything by doing this? At least at genus 0, have we gained anything? Well, I would like to say that yes. So now we have punctures that can be on the upper sheet or the lower sheet. And I would like to say that these punctures, if they are on the lower sheet, they correspond to particles that are incoming. If they are on the upper sheet, they correspond to particles that are outgoing. How can I support that? Well, let me introduce a parameter, lambda, here. And this parameter turns out by the scattering equations to be related to this invariant. And if we go to the factorization limit, the two split. Now you can start from here. In field theory, you will be surprised that such a thing can be connected to any other structure. So you start with this. You get this picture. Now you open up the branch, and guess what crossing happens to be? Well, literally, you cross these things, and you put them on the upper sheet, and you get the picture that we're all familiar with. Now, my last example, because Nathan is telling me that we don't have more time, otherwise we could go to genus 10, is genus 1. So here is a curve, here is a form. This is our standard genus 1. I'll only have the points on the upper sheet. So here are the embedding equations, and the scattering equations turn out to be this. What I would like you to remember for the next slide is the following, that L squared is proportional to lambda, the parameter that appears here, that degenerates the curve. And the other thing that I want you to remember is that these objects, all these equations, even though they look complicated, they are all polynomial equations in the end. Isn't that interesting? They are polynomial equations. There are no elliptic functions, nothing. They are just polynomial equations. If you solve them, you will just get something evaluated on the space that is defined by the coefficients. And we will go back to this in a second. So here are the observations. As I said, these are all polynomial equations. L squared is proportional to lambda. So could this L be the loop momentum of a loop amplitude? Now, any integral of the form, schematically given like this, would therefore be a rational function of these kinematic invariants, L squared and L dot k. Now the question is, can we construct loop integrands with this? And finally, let me end with some open questions. So what's the number of solutions? At genus 0, we know that there are n-3 factorial solutions. At genus 1, I don't know. So work has to be done to determine what's the space of solutions, how many of them there are. Is there a systematic way of constructing integrands? And now, this hyperelliptic construction is general for genus 0, 1, and 2, but can we generalize it to higher genus, where we know there are Riemann surfaces that are not hyperelliptic? And bigger questions, bigger font. Can general perturbative quantum field theory S matrices be formulated in this pre-stringy form? This looks like a string theory. And how can the pre-string form be deformed into a full string theory? Okay, thank you.
Actually, this is related to your last question. If you think of these scattering equations, it looks like, if you think of the graviton amplitude as a low-energy string theory amplitude, it looks like this is localizing the integral of the positions of the punctures to the saddle point. However, you might expect the saddle point to be relevant at very high energy scattering, as Gross and Mende pointed out. So why is it relevant for the low energy limit of the string theory amplitude?
That's an excellent question that I've been trying to answer for the past 8 months, and I don't know. maybe David knows.
No, I don't have it. I certainly don't. I've also, since I read your paper, been wondering about it. But in the higher genus case, we also found saddle points, which gave special hyperelliptic curves with, an interesting structure. And do you see anything special about those particular?
I tried, but I haven't. I know you found. I tried to look at the special configurations where the punctures go to the branch points.
Right.
And in fact, so that reminds me. Yes, I have a prize. Or well, no, the prize is for somebody who can. Sorry, it's not a prize. It's a challenge. That's a challenge. What's the prize? Oh. Sorry.
What's the challenge?
This one. Find a solution to these equations.
I think I didn't understand what was the conclusion in genus 1. Did you end up with a way to represent standard one-loop amplitudes as sums over contributions associated to solutions of the scattering equations?
So in a particular example, so we have been able to write the 4-particle n equals 8 supergravity amplitude at one loop in this particular form. We still don't know how to generalize it, but the statement I made at the end is general, that by summing over all the solutions to the hyperelliptic scattering equations of an integral that is a rational function of the variables will lead you to something that is a rational function that at least has a chance of being the correct object. So far, we have only been able to show that such a construction works at one loop for 4 particles. So it's modest progress, but...
Did you show us the relevant formulas?
No, I did not.
Fine, thank you. That explains something.
I only showed you a schematic version of the object.
Similar type of questions about the loop amplitudes. Do I understand correctly, again, that the variable L that you tentatively wanted to identify with the loop amplitude is fixed in terms of the location of the branch points?
No.
The equation doesn't fix it.
No,
so
it's the other way around. If you fix the location of the branch point, knowing the loop momentum. So you integrate over the loop momentum, and then of course the the Riemann surface will change.
In the process of integrating, but I could do integration, change of integration variables, and then for a given shape of the surface, fix the loop momenta.
You could, well, you're supposed to integrate over the shape of the surface, but you can change the orders of integration if you wish.
Right.
Yes.
But in string theory, what happens is that you integrate over loop momenta, and then you get a modular invariant partition function on the, so you're integrating once over the invariant moduli space of the Riemann surface.
Yes.
And then typically we would say that modular invariance is why string theory has finite amplitudes. Is your integrand modular invariant?
Now here, modular invariance in this particular construction doesn't actually impose a constraint. So, and it's field theory. So we don't expect we don't expect anything. Yes, in fact, as I said, the construction we have for the 4-particle amplitude works in any dimensions. So I would expect to find formulas. Well, as I said in the previous slide, the dream is that there is a pre-stringy way of reformulating quantum field theory. So any field theory.
But so in your integration, you can find places where you have UV divergences and that are not.
Yes, definitely.
Right.
Yeah.
Yes, yeah. Can you give him a...
I had a further question, which was whether the loop momentum, when you get your one loop amplitude, does the loop momentum come from the regular term that you can add to the differential?
From the regular, it comes from the, yes, the loop momentum is precisely the holomorphic differential. It's the coefficient of the holomorphic differential.
And naively, you have to decide where you're going to integrate in the end.
Yes, that's a very good question. So, and then you could ask, well, even when you write down a loop amplitude, what do you call the loop momentum? That's an integration variable. Well, it turns out that the answer turns out to be that this loop momentum, as I defined, happens to be the loop momentum of a completely symmetrized integrand. So there is a reason I didn't include it in this talk, which is that it's still in the process of being understood. But it seems that this loop momentum, or even when you pass punctures down from one sheet to the other, you shift the loop momentum by something that is proportional to k. So the only meaningful object that you can call the loop momentum would end up being, in the field theory, where you have several diagrams, a completely symmetrized object.
Okay.
Okay, so if there are no more questions, let's thank Freddy again.